We'll give a second for Billy to join.
Hey,
Hey, Billy.
sorry. How's it
Hey,
going?
no problem. It's going all right. Thanks for joining. We're like literally just about to get started. They downloaded the R Markdown files, and we're just gonna follow along with the videos. Um, so what I was gonna say is, I directed them to line 92, and you'll see in line 92 on the R Markdown script, there's like a YouTube link, and that's just basically the video that I'm showing on the website page. Are you able to see this website video now?
Uh, I am just re I'm just pulling the updated GitHub.
Okay, no problem. I actually don't know if I'm sharing the screen anymore. Let me see.
Oh, no, I cannot see the screen. Sorry, I thought you were
Okay,
talking about on my end.
no problem. Now you guys can see the
Now you're
screen?
good. Yep, you're
Cool.
good.
So because Helen's not here today, I think the best way to do it is we're just going to watch the videos and then try to work with the code and then watch the next video, try to work with the code and just keep going it from there. Um, but if anyone has any questions about like what the code is doing or if it's not working, although it should work since you guys all downloaded the R Markdown file, we can just kind of go from there. Does that sound good?
hmm Sounds good.
Okay. I'm gonna play the first video. We'll all just watch it
I think no sound, Steven.
What's that?
I can't hear any sound. I don't know if
Oh,
Yeah.
just
really?
yeah.
What would be the best way to do this then?
So if you click share again, I think there's an option to share with sound.
Oh,
Um,
really?
yeah, just to double check. It's on the right side under options.
Oh, I didn't know that was a thing. Okay, that's good to know.
Yeah. Yeah, so I think if
Okay.
you just reshare it with that, it should work.
Oh, so it's just like asking me for my password.
Um,
Can you guys see it now?
hmm
Okay.
No, I mean I can't. Yeah, you haven't played it yet.
I think it like disconnected from my headphones. Wait, can you hear me
oh,
now?
yeah.
Okay.
We can hear you. I think Joseph was just talking about the video. This hasn't started
You
playing
can't
yet.
see
So
the screen?
we can see the screen. You haven't. Joseph was just mentioning like you hadn't started playing the video. So
Oh, okay, gotcha.
yeah,
All
yeah,
right,
yeah.
I'll restart
No, you're all good.
it. Okay.
Fine.
Hi, everyone. My
There
name
we
is
go.
Helen Schmidt, and I'm one of the co-directors of the Coding Outreach Group here at Temple University. If you've clicked on this video or are following along with our live workshop tutorial, I imagine you're interested in making maps. Map making is an age-old practice, but today we'll talk about how we can leverage R, a computer programming language, to create and customize our own digital maps. Throughout this tutorial, we will cover the basics of map making, including design principles that are important to follow regardless of the medium you're working in. We will then pivot to creating maps using some basic and advanced R programming techniques, understanding geospatial data, and discussing how to leverage geospatial data to add features to a basic map. I'll then close out by sharing some opportunities to learn about digital cartography and take part in online mapmaking challenges. If all of this sounds interesting to you, I invite you to stick around for the rest of the tutorial. Before we get started with any map making, let's go over some key concepts like defining cartography, outlining key features of maps, and detailing what I mean when I talk about geospatial data. Cartography is the practice of making maps with the goal of communicating geographic information effectively and creatively. When you think of early examples of maps, these were often hand-drawn using information gathered via surveying techniques. Today, maps are much more accurate geographically, using images and data often gathered from satellite imagery. A single map obviously can't contain all the geographic information in the world. Therefore, when making maps, map makers need to strike a balance between what information to focus on and how to subjectively, yet creatively, design their map to make that information understandable for those who are looking at the map. It's important to realize that all maps contain some amount of bias as a result of these design choices. Take the Mercator projection as a classic example. In order to project the round Earth onto a flat two-dimensional surface, this projection enhances the size of land closer to the poles, so the North and South Pole, and minimizes land that's closer to the equator. This projection is widely used and widely criticized today, as its disproportionate representation of areas like North America and Europe can imply greater power and importance. With this in mind, there are a lot of decisions that one must make as a mapmaker. Let's review some key elements that you may want to manipulate or consider in order to help your map tell its story. Let's start with scale. Scale reflects the relative area depicted in a map relative to its real geographic size. You can think of scale as a compromise between the amount of detail in a given area and the expanse of geographic information that you want to show. A highly detailed map showing certain species of a flower may be more zoomed in on just a few square miles of land, whereas a map that's showing historical, political boundaries of a country may be less detailed and more zoomed out. Coordinates are also important to consider when making maps, especially from the technical side. You'll find a lot of maps using intersecting planes of latitude and longitude to reflect locations all around the Earth's surface as a data point of these two values. But because the Earth is round and most printed maps are flat, we need to find a way to print these curved features onto a flat plane. That's where projection comes in, a common example of which is the Mercator projection, as we discussed previously. There are actually a lot of types of projections, and you'll find that some countries tend to favor one over others when it comes to designing and developing maps. We also need to consider our use of symbols to describe certain elements depicted in maps. Depending on the information you're trying to convey, certain shapes and symbols may be more appropriate than others. Finally, one of my favorite parts of map making is considering color and typography. Color can be used creatively and functionally to emphasize certain features. A simple map can easily become more striking with the change of a color palette. Similarly, text can make it easier for viewers to understand the information that's conveyed in the map. Now, you may be thinking, how do we actually take all this information and create digital maps? We can use a type of data called geospatial data, which contains location-based information about objects and events that are associated with physical locations on the Earth's surface. This type of data is informative, albeit a bit complex, but we can leverage specialized programming packages in R to neatly extract this geospatial data and create professional-looking maps using a tidyverse approach.
Okay. Should I keep sharing with the sound, or should I toggle back? Does it matter?
Are we, you plan to go through the R script?
Yeah,
Or-
there's like other videos too.
Yeah.
Hold on.
So,
I can
sorry,
like
but I mean,
barely
like,
hear you guys.
oh,
Let me switch.
yeah. Yeah, why not?
Okay, can you
I
just hear me
think
now?
unless you're playing one of the videos, you could turn off the sound, I think, because we'll have to switch back and forth with the R script anyway.
Say that again. Sorry.
Sorry, guys. I said unless you're jumping right into another one of the videos, I think it's fine to not share with the sound if
Okay,
it's
cool.
reducing how loud it is for you.
I agree, yeah. Okay, so I think, and again, we can figure out the best way to do this. I think there's like a good degree of like R chunks to work through from, let's say, line 95 to the
Mhm.
next video, which is line 228. So I think the way I was thinking about it, but we could do this differently, is like we can just work through those R chunks for the next like 5 minutes or so. Let's see if anyone runs into any problems or has any questions about it, and then maybe within a couple minutes we can like get together and debrief on kind of what we did and move from there. Does that sound good?
Yeah, that sounds good.
Okay. So let's try to tackle, I think it starts with line 95 and we'll go all the way to line up 228, and then I'll check in a few minutes.
Sorry, could you repeat that? Repeat your last, please.
Yeah, I think like we're gonna go through lines 95 through 228 on our own, and then we'll regroup like as a group and check in about what the code did and see if anyone had any questions or anything like that. We'll just let everyone work on their own for a couple minutes.
Okay.
And Helen did like a great job annotating each R chunk, so you can just refer to the instructions before each R chunk to sort of inform you on what's going on.
Yeah. Yeah, she definitely added quite a few pretty good comments, which I think makes it easier to do like independent work over.
I want to try doing this with some other like random country, but
Yeah, I don't know if I'm a map making pro, but it seems like there's a lot of
yeah.
different ways to go about this.
There is, yeah. And there's if you ever wind up wanting to get started and not knowing where to start, I do know ChatGPT is pretty good with the map making tools in R. Um, I know I'm always like directing people to ChatGPT or some like other like AI for coding, but I I recently was using it to do it was a map of data involving involving executions in the United States. I don't remember why I was doing it. I was curious about something and it was like looking at the death penalty and stuff. But it was great. I had like I told ChatGPT what I wanted to do and it like gave me all these tools to make maps.
Yeah,
And
this is an interesting opportunity for a follow-up doom scrolling study. I think he just pitched.
yeah, yeah. And now my attempts to visualize the death penalty are forever recorded in this recording. Uh, but no, yeah,
What's
this is great. Oh, sorry. Go ahead, Steve.
wasn't gonna add anything valuable. Sorry, go. Keep going.
No. I was just going to ask if people were still working through it, or whatever. I was able to run through all of it and get it to work and it looked good. But yeah, any questions so far? Any difficulties?
From my end, none. Steven, you said to line one, like 145, right?
Line 228.
Oh,
No, so I'm still going in
Yeah,
that case.
it's okay. Maybe
No,
we'll
I
give
yeah,
you.
could
no,
still
there's
have a
no
couple other
rush.
packages
Yeah.
because I just started using R on this computer.
No,
So
no problem. Yeah, there's no rush. We give people like another 2 or 3 minutes. It's okay if you don't finish because we're gonna. I think it'd be helpful to just quickly maybe go through each chunk just to get like a quick gist of what it's doing.
Yeah,
Um, make sure we're all on the same page.
okay.
I think we're doing plenty good on time. So definitely take your time.
okay. Um, Um, I don't know. Okay.
That's good. Danny, how are you doing? You still working through it? It's okay if you are.
Yeah. It's all making sense to me. I'm just reading carefully to try to understand how it's doing everything.
Yeah,
So,
no, no.
Yeah, for sure.
I just realized I skipped a video. I thought the first video we watched was the first video. It's not.
That's okay.
I'm so sorry. I'm so sorry, Helen, if you're seeing this in the future.
It's okay. It's very difficult trying to run one of these without the actual person who made the workshop here. uh, was it just that one? How long is that video? It might not even be worth it if
No,
with 8 minutes.
I thought that video was the one in line 92.
No, it's okay. I when we've done these in the past, and people couldn't make it, I've like sometimes had people just go through it on their own. I'm pretty sure that this is just going to be her going through the individual lines. So I think
Yeah.
if we've already done that, well, I think it's fine to skip it.
Okay. So
Yeah.
sorry.
Yeah, because this is just all the stuff we just did, right? I
Yeah.
think.
you wanted us to go up to which line? Sorry.
I was just up
To
to the next, yeah, up to the next video, which is line
Yeah,
228.
okay. I'm there.
Okay, cool. I think let's take some time to, you guys can still see the screen or no? Yeah,
right.
right? Okay.
Mhm.
So I'm just gonna kind of go through each chunk and just try to hit like the main takeaway. But if you guys have any questions or if you just want to take some time to break down the code a little more, just let me know. Um, so the first chunk is just loading the relevant packages that we'll need in order to do some of the functionalities that we're going to use. Helen, described what each package is doing pretty briefly here. So hopefully that made sense to people. Um, Then in the next chunk, we are making our first map, and we're just pulling this like USA map data that the ggplot package like naturally has, and we're basically creating a data frame called USA underscore map. We're using this nrow function to just print out how many rows there are in that data frame, which is about 7,000. And this is just like a snapshot of some of the rows. And as Helen mentioned, there's 7,243 individual data points, and we're going to focus on the long and the lat variable, where the long variable is the longitude and the lat variable is the latitude of each data point. So we're just sort of feeding that into the ggplot function, where x is long, y is latitude. But importantly, I think the really cool thing about this code that I didn't know is this geom underscore polygon function that allows us to plot the data points in a way that's the shape of the actual US map, which I think is pretty cool. Not too knowledgeable about like the specific under the hood details, but it seems like that argument's doing some really cool stuff. I don't know, Billy, do you have any thoughts on that? Okay.
No, yeah, it's a pretty cool function. I believe the geom polygon you can use for a lot of things. I think that the USA map the USA map thing comes specifically from the map library. I could be wrong about that, but
Okay, that's good to know
uh
though.
yeah, but yeah, it's cool.
Cool. I'll keep it. Um, then again, we're using this head function to just print out the first few rows. Okay, what we're doing is we're pulling the data set called us.cities, and we're just printing out the first few rows, excuse me, from that new data set here. Then what we're doing here is creating a data frame called capitals that subset only rows in this US city data frame that are sort of defined as a capital, such that the capital column in this US city data frame set is equal to 2. That's how we know that it's a capital. And we're also not taking any rows that reflect Hawaii or Alaska. So we're going to end up with a data frame that's only capitals and has like only cities, only the capital cities of each state, and then there's only 48 states because we removed Hawaii and Alaska. That making sense to people?
Mhm.
Okay. So yeah, as Helen says, we have 48 state capital data points that we're going to basically plot onto this US map shape. And she's just highlighting them in white here. So it's basically kind of like stacking two plots on top of each other. The first plot was the shape of the US like shape, and we're just plotting the individual state data points on top of that. Basically just using the longitude and latitude. So this is like for each capital. Okay. And it looks like we're just basically subsetting the top 10 capitals by population size. And I think here it's just taking how many rows we're going to take and just ordering by which column, like sorting by a certain column. Here we're sorting by the top column, so we're just taking 10 rows sorted from like greatest to smallest population size.
I have just like a quick question. This
Yeah.
when we are the step previously where we took the points from the
Here?
maps. Yeah, where we're basically taking the points that we got from the maps
Yes.
library from USA map and then plotting them onto the geom polygon or the GG
Yes.
plot. That only like works because those two are like coordinate like the map from GG plot and the USA cities and the maps USA cities are like somehow already coordinated, right? Or
Exactly. Yeah, I think you're right. Basically, like the longitude and latitude would have to work like within the same space, or else they would just be plotting in like these random points. So all we're doing with this line is plotting what we did before, right? And you can see that here.
Mhm.
So it's like empty. But then because I'm guessing these two data sets are interrelated, like you said, because
Mhm.
we subsetted the capitals the way we did earlier, we're just basically sticking those on top of the first plot. And that's why it works.
Gotcha.
Yeah, basically just that map data library has all this stuff positioned in like some sort of a specific geographical structure or like through kind of like some like sort of two-dimensional structure. And it retains that structure even if as you put it into like a data frame and all that stuff. We could actually probably if you have the RStudio open,
Yeah.
in your environment, you should see the data frames for this stuff. You could actually click on like USA map and you see like the specific coordinates, like in longitude and latitude for different regions and capitals and stuff like that.
Yep, exactly. You should be able to open up the USA underscore map data frame and the capitals data frame if you want to just do a quick like
Right. I could
contrast.
see that they're
Yeah,
organized
and then
similarly.
so all of those latitude and longitude coordinates correspond to points on this 2D plane that Steven has visualized, like right here.
Makes sense.
Cool. Good question. And then yeah, this is just some sort of data wrangling in terms of like subsetting. So the next what we're going to do is like we have a data set containing the 10 most populous US capitals. We're going to use this geom label repel argument here, which is going to just draw a rectangle onto the text and make it easier to read. So I think this does a really good job sort of visualizing the text for the 10 most populated capitals. And we're doing so via this argument right here. So all we're doing is as the data, we're feeding in the pop data frame that we created earlier. And again, just feeding in the long and lat variables. And for the label, we're doing the name, which is right here. And then what Helen's saying is next we can like make this map look even better by using colors to make it like which data points reflect the most populated capital cities. And all that we're doing here is basically creating a new data frame called top 10 that's just only the column top name. I think that's what's happening.
Mhm.
And then all we're doing is okay, all of the ones that are not in the top 10 get assigned a 0. Any of the capitals that are in the top 10 get assigned a 1. So that way it's a binary variable. Either you're a 0 or a 1. And that's going to kind of make up our color scheme. So you can see now we're feeding it right here with this argument, where I think before the color was white. Yeah, before the color was white. And now we're saying the color is top 10. So you can see the top 10 most populated capital cities are going to have a 1, which is this like light blue color. Everything else is going to get a red. So it's just like another way to sort of make it a little bit more clear which cities are the capital. Okay.
Okay.
And now what this is doing here is just kind of customizing it even more with different ggplot aesthetics. I think there's a few going on here. I don't think I've encoded all of them.
I know one thing we are doing is changing the size of the point proportional to the population in each of them.
That's really cool.
That's what is right beneath polygon, I believe, where you see size equals pop times 0.1.
Here. That's super cool.
Yeah. And yeah, and then the other stuff is sort of aesthetic. So we are kind of cleaning up that label with geom label repel. And then specifying color values manually on the line right below it. The chord Cartesian argument effectively just make sure that we have everything fully within scale. Like you could see all of it and there's nothing outside that we're like cutting off or something like that. I actually don't think you probably need that argument there. It would probably run the same without that, but it's good to include it just in case.
Yeah, I'm not too familiar with the argument. Like I didn't
I-
know what it is until what you just said 10 seconds ago, but that's good to know.
Yeah, so the way I've used that in the past, and I don't know if maybe it has another use, but like you can add an X and a Y argument and basically tell it where you want the visualization to cut off.
Gotcha.
And there are other ways to do that, but I can't remember them off the top of my head. But if you use those other ways, what you actually do is like exclude data from the data frame. And then like if you're making a regression, then it changes that line, which you don't want to do. With this, you're
Gotcha.
like, all the data the same. I just want to focus on this. I want to zoom in on this part.
Okay.
Yeah.
I have a quick question about the block before this one.
Yeah.
Just how it assigned the things in the top 10 to blue and the others to orange. Is if you assigned a color to a column, does it just know to differentiate?
Yeah, only because there's a probably better way to explain this, but in that top 10 column, there's only a 0 or a 1. So there's only two color options. And R only has like two default colors that would apply to that. Let's say we wanted to divide it up in three somehow, like a 0, 1, or a 2. There would be three colors, however we
Okay,
differentiate.
gotcha.
And I think it might also be important to know with that argument, we're not specifying what colors.
Right.
We're just saying these colors should be different. R automatically chooses the colors. We're just saying we want different colors for these two groups. But if in the next chunk that we were just looking at, we do actually manually specify the colors with that scale color manual argument in there.
So here.
Mhm.
Right.
Yeah, that's why
And
this.
you can actually tell that the colors are slightly different between that visualization and the one right above it.
Yeah. Well, does anyone have any questions before we go on to the next sort of section? Okay. I think I'm just gonna play the video. Let me see how long it is. Okay, it's 17. There is like, would it be okay to do like at 1.5 speed? Are people okay with that?
Mhm.
Maybe not. I just think to keep things going a little bit faster. I think I'll do
Yes.
that. If we need to slow down, we can slow it down. Let's see how fast this is.
Okay, so now that we've had some practice making a map with ggplot.
Is that too fast? 1.25, would that be safe?
We could do 1 point. I could also walk us through this section if you think
Oh,
that
if
would
that's
be
easier, yeah, we could also just do that. I just didn't know. I don't know
okay.
what the is.
Yeah, no, took a quick look through this, so I think I'm okay.
You
Do you mind
share
if
this?
can I share my screen? And I can walk us through this. Thank you. Okay, cool. So can you guys all see that? Hopefully
Yes.
not
Yes.
as pretty as
Yes.
the website, but we could at least interact with it. Cool. So we're going to be using some different libraries here. SF, which stands for Simple Features, and then this OSM data library. So we're going to go ahead and run those. Cool. And so the first thing that we're going to be doing is basically querying our data with this OPQ argument. I believe that this is coming from, let's just double check. I think it's coming from this OSM data thing, but I could be wrong. Wrong order. Um, there we go. Yes, correct. So what I just did there, just the two question marks, OPQ, and we could see that it is coming from this OSM thing. So the term query, you might have heard that if you like did Katie and I's SQL SQL workshop last year, or if you've ever done SQL, when we say query, all we're saying is like we want to like subset a certain amount of data. We want to like ask for specific data rather than get like the entire data frame, right? So what we're effectively doing here is just like looking for data related to Zurich. We're going to try to visualize Zurich's roads here. And we are looking specifically for highways, and we want it returned in this simple feature format. And then we're also going to do one for water as well. And we're going to save these as Zurich roads and Zurich water, which we should be able to run this and hopefully get that visualization. Like Helen said, it does take a little bit of time. But as soon as we get that, we're going to go ahead and use the geom SF argument in ggplot, which also comes from this library.
Do you like zoom in?
And we're just gonna oh yeah. Oh, sorry. I get complaints all the time about how how tiny my
I
text
just
is. Give me
thinking
one
like
second.
for the video.
Why is it not coming up?
I thought yeah, just in view it should be.
There we go. Yeah, thank you. How's that? Is that any better?
Yeah, maybe like one more. I think that's better. Is everyone able to see it?
That's better? Okay,
Yeah,
cool.
that's good.
Is that look good for everybody else? Okay, cool. Sorry, I should have ran this beforehand. I didn't actually realize it was going to take as long as it is. But let's give it like another minute or so. And yeah, all that we're doing here, we're just feeding it this data. Again, that data is going to pop up in our environment here as soon as it's ready. And we should be able to actually take a look at what that is. While we're waiting for this to load, any questions, Danny or Joseph, about like what I've done thus far?
No.
Okay. Yeah, I think that this code looks a little different than what you might typically use in R. I mean, like this is if you've seen piping before, this is sort of like a different pipe that I think is specific to this library. But it's effectively the same thing. You know, we're saying we want to look for this data, we want to actually subset it more by only looking at highways, and then we want to remove some of the more complex features, just to simplify it.
Can you like type another example of a pipe? Just because I know like I may not have
Oh,
mapped that language onto what it is in R, but other people may have come across this in R. Yeah, like that. Like you may have seen
yeah,
that
yeah.
in
So
other
this,
apps.
This is the typical pipe. There are a ton of them. They typically are used in like the tidyverse, sort of like way of working in R. You might have also seen like within is another one. There's a few of them, and they actually do make things a lot easier. And they pop up in other languages too. Like I think in Bash, just this line is itself a pipe too. You might have seen them elsewhere. Oh, there we go. I think we're done. Or it's only because I typed in this block. Yes, it is still working. I really wish there was like a progress
I have
bar.
mine. I have
Yeah, you know
mine.
what? Oh, sorry. Yeah, I was gonna say we can let me go to the website. We can just assume that this loaded. We don't have to like run this live. Given that Steven took the time to make this beautiful knitted file. Okay. All right, let me reshare this now.
Danny and Joseph, do you guys has it plotted for you like the map of like the roads in the water?
Yes.
Okay, great. Yeah, so this is ideally if I did run it ahead of time, this is what we would have seen eventually, right? Which is great because I mean it is some representation of all of the roads and the water, but like this is virtually unreadable in this current state, right? It's just this kind of like box of black squiggles. And so we can wind up like sort of cleaning this up a little bit by like specifying some specific latitude and longitude that we want to look at. Here we go.
Yeah, those are coordinates are the center of Zurich, and we're just gonna basically define like a radius, a circle around it. So in order to do
Yeah.
that, we have to find the centralmost points.
Exactly. Right. And so we create a tibble. You guys might have seen tibbles before. I mean, it's effectively like a multi-dimensional array or a data frame. It's just going to contain, it's basically taking this same thing and then putting it in a slightly different structure that's going to work with the SF thing. So then we run this this argument, which projects it into standard coordinates. We're just going to feed it the longitude and latitude values that we have right here. And we're again, you see pipes here that we're going to be running. Oh, this is the radius of the circle to say how wide that we want the circle to be. We're going to transform it back to standard coordinates. Let's see, forgot this part. Ah, there we go. Yes. Then we're going to basically zoom in on that circle. We're going to visualize that circle, which we have right here. We're going to include the water and crop out only the water that is contained within this circle. And then we just go ahead and visualize it. You can see that we fill the water data with blue. Everything else we're leaving black, and all the empty space we're just leaving white. We again do the void theme, so it's just all white around it. And then we have this much more legible representation of like center city Zurich, right? Where we could see all of the highways, we can see the waterway clearly running through it. And yeah, so it just is a good way to like represent the data that you actually care about and zoom in on it and eliminate all of that like sort of extra noise that we were seeing right up here. And
Yeah.
you can kind of like see that you could see where this comes from if we're like looking right at this center part right here.
Yeah, there's just like a two-step phase, maybe is like a different way to think about it is like we saw how, it looks in the beginning, then the first thing we did with all those coordinates where we're, projecting the coordinates is we're just figuring out how to define a circle around sort of the center of Zurich. And the next step is we're just defining the intersections for each road. And then we're kind of just plotting that in a way that looks really nice.
Mm.
in that chunk right there.
Yep. Any questions about that part? No. Okay.
No.
I think next it's like a challenge or like an exercise. We're gonna try to sort of do our own thing with a different city. So maybe
Yes.
we can take some time to do that. Let's take like 5 minutes to give that a try.
With Interlaken, yeah. I don't know if I'm pronouncing that right.
Uh,
Oh, there we go. Now it wants to come up. Okay.
So with this challenge, are we just supposed to run it, like run the codes there? Or
no,
are
so
we
the code solution is the answer, but the original like the way to do is just to try it on our own before we do that. So like in case it helps to start, like what I was doing is you can just copy the lines 254 to lines 267, that chunk. We're just going to substitute Zurich information with the capital of Interlaken. Does that make sense? So it's kind of doing what we just did, but with a different city.
can you repeat what you just said?
Yeah, so like the exercise is now let's try making a similar map to the one we just made using a different city. Instead of
Mm-hmm.
Zurich, we're going to use Interlaken. I may be mispronouncing that. So how I was approaching it is if you copy line chunk like lines 254 through 267, that's where you can start from, but we're going to have to replace Zurich with this other city that we want to do and just go from there.
Okay.
Does that make sense? So
Yeah.
really, all you'll have to change is like instead of Zurich roads, let's say Interlaken roads. Instead of Zurich, comma ch, we have to replace that for the arguments needed for Interlaken, and I think it's Switzerland. No problem, Billy.
Okay. Okay. Um,
The highway and the water arguments can change because we're plotting. I mean, can stay because we're plotting the same things. And Helen mentioned in order to find the city center coordinates, you just have to do a quick Google search of like what those coordinates would be.
mm,
Give people like another minute. I'm still working through it, but I think we'll be able to meet as a group and talk through it together.
It's just on the calendar. Pretty sure it hasn't been here for a while. I'll see.
All right, I'm gonna share my screen and we can go through it together. We can see what arguments we changed versus kept. So the first step is like what I was talking about before. I just copied this argument or these two commands, and I just changed all the Zerg information to be interlaken. Did that for the roads, did that for the water. This stuff stays the same because we still want to plot the roads and the water. Okay. And then that's what we did here. So I'm just plotting these objects now. Just again, replace the Zurich stuff. Substituted that. And it looks a little bit not how we want it to look. So we're going to try to build it up from there. Then I just Googled what the city center coordinates were for Interlaken. I got these values. And then here, my understanding is like we're just kind of standardizing the coordinates in a space that's conducive to be able to plot it. So all I did was, again, just change the data frame that I'm feeding it into. And I just created a new data frame from that. So it didn't really touch anything here. Just changed the data frames that I was referencing. Then here again, we're sort of defining the intersection between the roads, the water, and the circle. So again, I'm feeding in, I'm creating these data frames, but I'm feeding in the circle that we defined earlier and the roads that we defined in the beginning. And then the water that we defined here. And then we're just putting it together and plotting it like we did before. And you should get, and you get this warning message, you can ignore that. We plot it all together. You get this really cool map. Honestly, it didn't take too much to get this map, but it looks really, really nice. And then this is the map for the city. Did people run into any issues with that, or did anyone have any questions about the code and how we got there? I know it's a little bit new. Hopefully it makes sense for the most part.
The one thing I'm not really grasping is
Mhm.
the code when defining the circle, like the tibble and then filling it in.
Yeah.
I don't really know what that's doing, to be honest, but
Yeah, I think I'm definitely not like probably the best person to explain this, but to me it feels like we're first getting the radius. We're like defining a circle around the latitude and longitude of the specific city. But all of these arguments, I think, are literally just like transforming it into a unit that this R package can understand in order to plot it in the way that we want it. So I know it's like not a satisfying answer, but that's like my interpretation of it. Yeah. I don't know, Katie, do you have any thoughts on just doing anything different? I just am not familiar with this.
Yeah, I was trying to see exactly what CRS is because I think, yeah, it's the common reporting standard for something, I think.
Yeah.
But I think that's what it's just taking the data like you're saying and sort of, is it multiplying it
I think also like I'm sure Helen describes this, very
in the
nicely.
video? Yeah.
So maybe that's on us, but I'm sure it's in the video.
Yeah, it's just basically defining the whole circle around it. And it's unfortunate that like it would be nice to know. Yeah, she probably says what the 4326 and the 2056 numbers are.
Yeah. But I think for the sake of time, we're just gonna keep going. Hopefully that made sense. The code's here. Let me toggle back to the index file.
Oh, I figured out what those things are.
Oh, what is it?
So the 2056 is the Swiss coordinate system.
Hmm.
The buffer is a 2,000-meter buffer. I can't figure out exactly the the 403026. It's saying convert to spatial feature with WGS 84 CRS. I don't know exactly what that means, but
Yeah, I don't know. Saying the standard CRS is 40 through 26, so that seems like it's just, I don't know, something that like doesn't need to change. I
yeah.
think everything else we just have to define ahead of time. That's good to know. Um, I think I'm just gonna do a Billy's head and go to the next chunk so I can share that, share my screen here. Okay, so we are here, section 3, online open data. Helen has another video there that you can reference that I'm sure describes it in ways better than I will right now. That's okay. So basically here we're just loading in some extra packages that we'll need for this section. We're going to read in an Excel sheet here, and we're just going to call this data frame avalanche. Here's like the preview of what a few rows look like. There's 19 columns, 6 rows are printed. Okay, Canton level data. This is map stuff beyond my expertise. It sounds fancy. I don't know what a Canton is, so I didn't make it very far here.
It's okay. I was gonna say the video for this one isn't that long if we do want to go that route.
Yeah, I think that would be
much shorter. It might be better off.
Okay, let me reshare with the sound on. Okay, I'm gonna play the video.
One of the best ways to find publicly available geospatial data is to access online open source databases. There are hundreds of these types of databases that are specific to geospatial data. Local and federal governments often have open data resources that you can find by searching the name of the city, country, municipality, plus open geospatial data in any web browser. When you find these databases, you'll often find a variety of data file types, including CSVs and shapefiles. Depending on the type of map that you want to create, some data forms might be more helpful than others. For Switzerland, I'm going to use a website called NVDAT to download some free publicly available environmental geospatial data. Between this website and opendata.swiss, there's a lot of data to work with, especially for Switzerland. So I highly encourage you to download some other data and explore how you can map it after finishing this tutorial. Okay, so going back into our script here, the first thing that I'm going to do is load a couple of new packages. So the first will be a package called read Excel, and that will just allow me to load in some Excel data nicely. I'm also going to load our geo boundaries package, which will allow me to get the administrative boundaries for Switzerland's cantons. So that's just the name for the provinces or states or kind of sub areas of Switzerland. They're called cantons. Okay, so from the data that I downloaded that is available alongside this tutorial from NVDAT, this data is highlighting different locations of avalanches in Switzerland. As many of you probably know, there's a lot of mountains and snow in Switzerland, so with that comes avalanches. So I'm just going to start by loading in these packages and loading the avalanche data set, which I'm just going to save as an object called avalanche, and then I'll preview it using the head function. From this data set, I can see an ID for the avalanche, the date that it occurred, the hydrological year, the canton, the coordinates in latitude and longitude, and some more information about the elevation, the slope aspect, the danger ratings, as well as number of people who died, number of people who were buried, and any sort of activity that may have caused the avalanche. So a lot of information contained in this data set. I'm also going to use the RGeoBoundaries package to get the administrative boundaries for each of these cantons. So I'm going to use the GeoBoundaries function from the RGeoBoundaries package, and I want to specify that I want the boundaries for Switzerland, and then I want my administrative level, or ADM underscore LVL, to be equal to ADM1. So that's basically saying, don't give me just the boundaries for Switzerland as a country, give me the next most specific level, which are the cantons. So I'm going to save that as an object called canton, and then just show that information from that object so I can see what I'm working with. So when I look at what the canton object looks like, I can see that I have a simple feature collection of a geometry type multi-polygon. And I see some groups, the names of each of these cantons, shape IDs, and the geometry column. So that geometry variable is going to be what allows us to actually create the map of these cantons. Now, in order to eventually match our avalanche data with this canton data, we need to change the canton codes in the avalanche data frame to the full name seen in the canton data frame. So I'm just going to create a new variable called shape name within the avalanche data set and just save a bunch of NAs in there. So when I do that, I'll just take a look at my avalanche data set. And if I scroll all the way to the right, I'll see I now have a new variable called shape name. Now what I want to do is in that new shape name variable, when each of the canton IDs, which are just stored right now as 2-letter identifiers, when those different letters are equal to certain combinations, I want to store the full name of that canton in my new shape name variable. So I just looked up exactly what these 2-letter codes stood for each of these cantons, and I make sure that my spelling and capitalization match the way that they're spelled in the canton object. So not the prettiest way to do this, but it is very effective. So I'm just going to highlight all of these different all of these different canton names and replace them in the shape name variable. So now when I look at my avalanche data set again, over in my shape name column, I should see that all of the avalanches that have a corresponding name in our canton data set also have the correct shape name in the avalanche data set. Now, like I said, we have some information on avalanches that happen in parts of Italy and France as well, because these are happening kind of across the Alps mountain range. So I want to only include cantons that are present in my avalanche data and remove all of those that are just equal to NAs right now, because those are not ones that are also present in my canton data. So I'm going to use the subset command and just make sure that I remove any instance of NAs in that new shape name variable. All right, and so then the final thing that I want to do is take my avalanche data and calculate the number of avalanches per canton per year. So I'm going to use a short piped statement and save a new data set called avalanche summary years. And I'm going to use my avalanche data set and group by the shape name. So that will be the full canton name that we just defined and the hydrological year. And I want to just do an avalanche count summary variable that just counts how many avalanches occurred during that year. So I'll run that section of code. And if I take a look at the avalanche summary, I can see that for each hydrological year and for each canton, I have a count of the number of avalanches that occurred in that canton in that year. Then I'm also going to calculate the proportion of avalanches that happened in any given canton across all these years, I'm going to calculate the proportion of all the avalanches that occurred in a given canton. So this is now more proportional to areas that may get a lot of avalanches versus areas that get just very few. We'll be able to actually directly compare them. So I'm going to do a little bit more of a complicated type statement and take my same avalanche data set and now only group by the canton name, calculate a same avalanche count. So this is just now the total number of avalanches that happen across all the years. And then I'm going to calculate the total number of avalanches and divide the avalanche count by the total number of avalanches to get a proportion of avalanches that happen in each given canton. So if I execute that line of code and look at the data, I can see that I now have all of my canton names, the count of avalanches that occurred in each canton, the total number of avalanches, which will be the same for all cantons, and then the proportion of avalanches that happen in that canton. Okay, and then what I'll do is merge this new avalanche summary total data set that I've just created with the proportion of avalanches. I'm going to merge that with my canton data by the shape name. So what I will wind up with is a data set that has my geometry from the administrative boundaries of the canton, and then I'll have a proportion of avalanches that happen in that canton relative to all the other cantons. Okay, so I have my final avalanche summary data set. So I'll go and look at that, and you can see that that's exactly what I have now. So I have all the information for the canton names and the proportion of avalanches that happen in that canton. And then if I scroll all the way to the right, I can see that I also have the geometry for that canton. So I'll be able to use this data set to not only create the canton boundaries, but also add some descriptive information using color about the number or proportion of avalanches that happen within that canton. So to do that, what I'll do is build a ggplot, and I'll first add a geom SF using the canton data, and I'll just fill it with white and put an outline of a kind of dark, almost black color, just to show the administrative boundaries. Then I'll add another geom SF, this time using the geometry variable from my new combined avalanche summary data set. And I'm going to fill each of the polygons that are plotted based on the proportion of avalanches that occurred in that canton. In order to tell ggplot which colors to use, I'm going to use scale fill gradient to show that lower proportions of avalanches are this kind of beige color, and higher proportions of avalanches are more of an orange color. And then, as always, as we're learning with all of these types of plots, with these SF geoms, I need to add in coord SF, and I'll just add in theme void to remove any sort of other plot features. So I'll go ahead and plot that, and I can see that for some of the cantons kind of in northern Switzerland, where, spoiler alert, there's not many mountains in that part of Switzerland, we have no data for avalanches. So no avalanches have occurred in those regions in Switzerland. But then we can see that we have two pretty dark red cantons kind of in the southern parts of Switzerland with some varying levels of beige and dusky pink colors as the different proportions are plotted.
All right. Can you guys still hear me? Yeah, okay. Hopefully that made sense. I think we can just do a quick review of the actual code chunks that we went through just to make sure everyone's on the same page. So again, we just are loading the libraries here, reading in this Excel sheet, calling it avalanche, printing out a few of those rows. I know she mentioned what a canton was. I can't remember, but this is us securing information about canton data here, and we're calling it canton. Okay. Now
it's like a province or like a state.
Oh, wow.
Sorry.
Okay.
Yeah.
No, it's good to know. Okay, cool. So basically, we're just creating a new column called shape name here. We're just defining an empty column here. Then we're saying in the shape name column, for any rows in the Canton column that are equal to XYZ, we're just going to name it something else. We're going to give it the full name, and we're putting that in the shape name column here. Okay. I think this part I'm a little over my head. It seems like we're pulling the avalanche data frame, we're grouping by this column, creating a count of how many avalanches in each canton. Does that sound right? I think we're getting the total number of avalanches and then the proportion within each canton. I think that's what she was talking about. Then we're creating a new data frame called avalanche summary here, and we're merging this data frame and the canton data frame by the shape name column. Oh man, wow, this plot looks so nice. Then we're just building the plot here using the GMSF argument, feeding in the Canton data frame, defining the fill and the colors here. Then we're using the geom_sf argument again, feeding in the avalanche summary data frame, the geometry column, and defining the fill according to the proportion of avalanches within each canton. And then defining some more colors here. And I think she's mentioning that this argument is required whenever you're using the geom_sf function. And then we're just using the theme void to get rid of the themes, I'm guessing. That looks so nice though. Does anyone have any questions about this? Or anything that we just talked about? Okay. I don't know if this is, oh, maybe it's just talking about the challenge. I think I'll just play this video.
Okay, so I set a challenge to try using the avalanche coordinates to plot the exact locations of all avalanches that took place in the 2022-23 hydrological year. I suggested using the Canton map that we already created and GeomSF to plot these avalanche locations. If you wanted a bonus challenge, which I hope that some of you are up to it, you can color the points based on the number of people that died in each avalanche. As a hint, I included a piece of code that you'll need to transform the latitude and longitude variables in the avalanche dataset to SF geometry. So that includes using the st as SF function. In the example code, I'm suggesting that you'll use the subset of the data, so only the 2022-23 hydrological year. You'll need to specify which variables correspond to the longitude and latitude variables in the data set to tell the STSSF function how to actually plot these coordinates. And I'm also saying that the projection for this transformation should be our kind of standard projection. So I'm specifying that CRS will be equal to 4326. Okay, so the first thing that I did to make this map as part of this challenge was to select only rows in my avalanche data set that had a hydrological year of 2022/23. So to do that, I just used the subset function on my original avalanche data set, and I saved that as a new object called avalanche 2223. Just to keep the data cleaner, this is not something that's entirely necessary, but just helps kind of keep track of everything that you will be using. I just selected the variables of interest. So that included my start zone coordinates, latitude, longitude, the number of people who died, the shape name, and the avalanche ID. And because these default variable names that came with the data that I downloaded are kind of long and annoying to type out, I just renamed the variables for ease and to be consistent with what we've been calling some of these things throughout the tutorial. So I've specified that the latitude will be called lat, the longitude will be called long, number of people who died will be num_dead. I'll keep shape name as is and just shorten avalanche ID to ID. Now comes the part where I'm using that hint code that I provided with this st as sf function. I'm using just my subset data, so the avalanche 22, 23. I'm specifying which variables are making up my coordinates. So like I said, you'll want the longitude variable first and then the latitude variable second. And just the way that I selected these variables means that longitude is actually the second column and latitude is the first column. And then I'm just specifying my standard projection space of 4326. So now I have a new data frame called avalanche underscore SF, and that's my new SF object. And if I actually go and look at that data set, I can see that I have 4 variables. The first is number of people who died. The shape name is the canton where the avalanche took place. The ID is the avalanche ID. And then I have a new geometry column that says point and has the latitude and longitude coordinates of that avalanche. So using this geometry point, I can actually plot all of the points of the avalanches using geom_sf in my ggplot. So that's exactly what I did. I first, on top of the existing Canton geom_sf that we already plotted, I added a new geom_sf using this avalanche SF data set. And I'm just telling ggplot that I want the color of each of these points to be based on the number of people who died. And the size of my point should be size 2, so just making them a little bit bigger. I also included my coord SF and theme void arguments just for ease of plotting and to make sure that the coordinates are being recognized appropriately. And I included the same scale color gradient with the low number of people who died in each avalanche being kind of a beige and the high being the same kind of dark orange. I also added a little bit of information to my theme, just specifying some changes to the legend and background of the plot that I wanted to make. So if I run this section of ggplot code, then I can see that I have a new map of Switzerland plotted. I have my cantons plotted, this time black being kind of the fill color and white being the outline color. And then each of these points reflects a different avalanche that happened in 2022, 2023. And I can see that there are a number of kind of darker red spots indicating more than one person tragically died in each of these avalanches. And then I have a bunch of these kind of grayish white spots that indicate an avalanche happened, but no one died.
Okay. So basically she just reviewed the solution to the challenge here, and I'm just gonna go through it really quickly just to make sure we're all on the same page. So all she's doing here is subsetting from the avalanche data frame. We're only going to take rows in this column that are equal to 2022 or 2023. Create this data frame called avalanche underscore 2022 underscore 23. Here, we're just subsetting specific columns that we're interested in using moving forward. And again, it's just using the pipe operator and just a different way to subset it maybe than what we traditionally see. Then we're just renaming the columns here. So latitude will be lat, start zone, blah, blah, blah will be long, so on and so forth. Then this is the argument that she's previewing here that we needed to change. So we're just feeding in the data frame that we just created. We're defining the coordinates where the longitude is reflecting the second column, the latitude is reflecting the first column. And we can confirm that's true just by looking here, seeing that the latitude was first, longitude was second. And then this is just feeding into that standardized projection space that we looked at earlier, 4326. And here's basically just putting the plot together, just building it from there, defining different color properties that we want to use, the data frame that we'll be using, all with geom_sf. And you can see it produces a really, really nice plot here. Yeah, I'm really impressed by these map making skills. It's super cool. Does anyone have any questions about that? Does that make sense to people? Okay. I think there's only one more section. It's like a different type of geospatial data she was saying. It's going to be elevation data. I'm not sure how long this is. Okay. We think it's okay to watch 9 minutes. Okay, so we'll just watch this one and then we can just review from there. Sound good? Okay.
The final type of mapping approach that we'll cover in this tutorial involves plotting elevation data. There are a lot of different ways to do this in R, including making 3D renderings, but one of my favorite and one of the most straightforward ways to do this is create what's called a contour map. Contour maps use contour lines, which are old cartography techniques that use line spacing and shaping to denote elevation changes on a flat two-dimensional surface. One benefit to working with elevation data in R is that there are a number of dedicated R packages that allow you to gather elevation data from anywhere in the world. Like OpenStreetMap, we can use administrative boundaries to define exactly where we want to pull elevation data from. We can use the same R GeoBoundaries package to get the administrative boundaries for Switzerland. But this time, unlike in the previous section, we're just going to get the overall country boundaries rather than the regional canton boundaries. So if I go over to the script, I'm just going to start off by loading some R packages that are useful when working with elevation data. So the first, I'm just reloading that R GeoBoundaries package, even though we just used it previously. I'm also loading a package called Elevate R, or Elevator, which is our crucial elevation data querying package. And then I'm also loading a library called Show Text, which will allow me to pull fonts from Google Fonts and load that into my R workspace and add some fancy text to some of my maps. So I've loaded all these packages, and now I'm going to use the same R GeoBoundaries function, just GeoBoundaries, and within that function, I'm just going to put Switzerland as a string and get that country level data for Switzerland. And I'm just going to save that as an object called Swiss. Like when we loaded the canton boundaries in the previous section of the tutorial, in that case, we had one multi-polygon for each canton. But this time we just have a multi-polygon for the entire outline boundary of Switzerland. And when we examine this administrative boundary data, we see our ever important variable called geometry, and that defines the geographic boundaries of Switzerland. We can use this in combination with the elevator package and get an elevation information only within these defined boundaries. And so in this case, that would mean that we're getting elevation data for all of Switzerland, but we're not getting any surrounding countries like France or Italy, even though we have this extended mountain range that crosses country borders. Since Switzerland is famous for its Alps, I'm going to save my elevation data into an object called Alps. We'll use a function called getElevRaster from the elevator package to actually pull this elevation data. And we need to define 5 different arguments for this function to get the data that we want. So first, we'll define the locations, which is the Swiss administrative boundary object that we just created. Then we need to define the zoom level, which will range from 1 to 14. You can play around with this to zoom to your liking, but I'm going to use a zoom of 6. We also need to define something called the clip, which is the thing that allows us to use the multi-polygon to clip the returned elevation data. We're also going to set an argument called neg to NA, and we'll set that to true, which will allow the getElevRaster function to change any negative values to NAs. And then finally, we'll define our projection and ensure that our data is in the WGS 84 latitude and longitude coordinates. And I've just included exactly how to define that projection. You don't need to worry about anything more about what all of these parts mean, but that's essentially what we're doing. The other thing to note, which will be shown in a warning message that comes up, is that the elevation will be saved in meters. So using all of this information together, I'm going to use the getElevRaster function from elevator and get the elevation information for my entire boundary of Switzerland. And I'm going to save that as an object called Alps. This will only take a couple of seconds to run, but if you increase your zoom a lot, so say you have a zoom of 13 or something, that will take a lot longer because it's getting a lot more precise information. Okay, so from this function, we can see that we now have an object called a large raster layer that our ALPS data is saved as. One thing that we want to do is convert this to a data frame and then remove any of our missing elevation values. So we're going to use a version of the as data frame function. So this is something that you'll see comes from a lot of different packages, but in this case, we really want to make sure that we're using the Terra package version of this function because that's designed to handle this large raster layer type of data. So I'm just going to overwrite the ALPS object and use my Terra package to specify that I want to convert ALPS to a data frame. And I want to also specify an argument of xy equals true. And then once I do that, I now will see that I have an object that has 3 variables and about 101,000 observations. And these 3 variables I want to rename to be my latitude, my longitude, and my elevation. So I'm just going to use the call names function to just change all of the column names all at once. And then I finally want to remove any missing elevation values. So I'm just going to subset this data frame and remove anything that is equal to an NA in that elevation variable. And we'll preview the first few rows of this. We can see that we went from about 101,000 observations down to 56,000. And in the resulting data frame, we have a latitude variable, a longitude variable, and an elevation variable in meters. So we can use this data in combination with a new geome called Geome Contour and create our contour line map. One thing that we need to specify with Geome Contour, especially to kind of represent our elevation increase in kind of a fun way, is we need to actually define the vertical height using our elevation variable. And we can color the elevation depending on this height using an argument called afterstat and in parentheses level in the color argument. So as our elevation increases, the color will change in the lines from one color to another. So to build this basic map, we're going to start off by adding a Geome SF using our Swiss data frame. So this will just, my apologies, our Swiss SF object. So this will just plot the administrative boundaries for all of Switzerland, and that will just be kind of in the default gray. On top of this, we want to put our geome contour, and we're going to specify that the data will be coming from our ALPS data set. Our X will be equal to the latitude, Y will be longitude, and our Z will be elevation. So that's the height of our contour lines. And then the color, which will be related to the height, we're going to use that afterstat level to increase or change the color of the line depending on the height of the elevation that we're plotting. And then again, because we have a Geome SF in there, we need to specify that our coordinates will also be SF. So I'll execute this chunk of code and we can see that we have our nice gray outline of Switzerland and we have our contour lines. So kind of consistent with what we were seeing where avalanches happen, we also see that these are the areas where there's increased elevation or the mountains where these avalanches are happening. And we can see this kind of ridge line of lighter blue as the lines kind of get closer together and lighter in blue color, that these are where kind of the tallest peaks in the Alps in Switzerland are. So we have our basic contour map, and now we can move forward to the final section and learn all about how to further customize these maps, which is arguably the most fun part of map making.
Okay. Did anyone have any questions about that? I think I was just going to go through the code like we've been doing before. Okay, so here we're just loading in again packages that we'll need for these type of plots. I think here we're defining the boundaries that we'll need for Switzerland using the geo boundaries argument from this package, and we're just feeding that data into an object called Swiss. Then here we're using this get elif underscore raster function, and there's like 5 different arguments that we'll need in order to sort of define what we'll want to plot. There's the locations, the z, which will plot the zoom. I think Helen was talking about. I think this one's from 1 to 14. She picked 7. The clip argument, this one, and then the neg to na, and then the projections one, which this seems like it's kind of a predefined projection space, because I remember seeing this WGS84 number in the plotting that we did earlier. And then here, Helen was talking about that we'll need to use this as data frame argument from the Terra package in order to work with this type of data. And then we're just renaming the columns here to be lat, long, and elevation. Just removing any sort of rows or values that are NA in this elevation data set, feeding to this object called Alps, previewing what it should look like here. And then what she's just talking about in terms of using geom_sf argument to plot the Swiss data set. Then here's, we're going to use the geom underscore contour function to be able to plot the elevation data. So it does use X, Y, and Z, whereas regular ggplot just uses 2D spaces and X and Y. And we're just defining the color for the elevation to describe the gradient and elevation here. And then because we're using geom_sf, we have to use chord_sf. And that's basically what we did. I know I zoomed through that, but does anyone have any questions about that? So far, so good? Okay. Not sure how long this one is. Okay, I don't think we have enough time for that, or it'll be close. So I was thinking we can just go through the codes together. That'd be okay?
Sounds good.
Okay. So the way I'm understanding what's happening here is, I think earlier she describes, now we have a basic contour elevation map as elevation. Oh, this was for this though. Let's see. Is it just like customizing it like aesthetically? Maybe.
Yeah, I think so.
We plotted this before. This is the Zurich map that we plotted earlier. Before it was like white and like light blue. But I think here we're just defining the aesthetics a little bit differently to make it look nicer. And then just outputting it and saving it and using G2save according to different properties that we want it to look like.
Yeah, exactly. I think that's right.
Yeah, this is all code that we looked at before. It's just being defined with different aesthetics to make it stand out a little bit more. And we're doing that with a few other plots. So this interlaken plot we also made earlier before. Again, it was white and sort of dark blue before. Here we're just changing the colors, the line with the fill and stuff like that to make it look nicer. And it does look nicer. And then we're just saving it here. Then this is the avalanche plot that we made like maybe 10 minutes ago. And again, just changing the aesthetics to look a little bit nicer. Trying to think of anything new that I didn't see before. I don't think this was there before. I'm not sure what this does. Does anyone know what this does? Okay.
What it does?
Yeah.
I think it just adds the labels to the scale on the right side.
Oh, that makes sense. That makes sense.
Yeah.
Maybe that was there before. I may have just missed it. Okay.
I think it was plotted by proportion before, so it's just changing up like how it's represented on the scale.
Maybe because the proportion's still here.
Yeah. So it is in proportion, so just representing it as a percentage.
Oh, I gotcha. And then the last one, this is the one that we just plotted before to do a quick contrast. That's this plot. And we're changing the aesthetics here. Oh, wow, this looks really nice, adding a little title.
Yeah.
And just representing the contrast, the elevation contrast with different colors. I know we blew through that, but you can definitely go back to check this out if you want to learn any more about it. Helen outlined some next steps in terms of like resources for sort of map making skills, as well as open data sets. And she did highlight this like a 30-day map challenge that I know she's partaken in before, and like you get to, I think it's like a month of generating a different map each day. And it seems like there's a big online community of sort of digital map makers that do this every year. So this is the 2022 30-day map challenge, which looks like really cool. Like I don't even know how they went about doing this one. This one looks really cool. Duncan location in Massachusetts is the most Massachusetts thing to do. Shout out Helen. And then this is last year's, I guess. So yeah, it seems like there's a lot of people who are really interested in doing this, and it's like a good community that outlines resources and sort of and data sets that you can work with for this. So hopefully that was helpful. I know it was a little different because we didn't have the host here to help walk through it, but hopefully we were able to walk through it in a way that made sense for the most part. But if you guys have any questions about this in the future, don't hesitate to reach out.